Well, if you've been thinking ahead a little bit, you may have already have heard of colligative properties. Some kind of property about a solution, a solvent and a solute, um, that gets changed as the solute dissolves in the solvent. Something about the solvent as a pure solvent. And I'll tell you the answers. You probably know them already. The boiling point goes up, the freezing temperature goes down, the the vapor pressure of the solvent decreases, reduction of vapor pressure, and lastly, osmosis. Um, the osmotic pressure is different with a solvent pure versus a solution. In any case, this little clip, I want to simply address the reduction of vapor pressure called Raoult's Law. I think I already have a Raoult's Law video, so why am I doing another one? I ask myself, but in case you want to see it. So if I have a lid on a beaker or a jar, I might want to make it airtight, but whatever. There's some force or some probability or some likelihood of some of that liquid evaporating into a gas, and pretty quickly I'll develop an equilibrium between the gas phase and the liquid phase where the airspace above has X amount of this molecule in it, and totally temperature dependent, because if I warm up this liquid, doesn't it encourage the evaporation, and so this airspace will be filled with increasing amounts of whatever this is, probably water, right? But if I put something into the water, like sugar or any other molecule actually, we say that at least at the surface where the interaction happens between the gas and the liquid phase, the solute particles actually occlude or interfere with or get in the way of that evaporation. So you'll notice this arrow has been decreased, whereas this arrow is the same size. By that we mean the amount of liquid solvent particles escaping into the gas phase is decreased because of the presence of those millions and millions and millions of solute particles, especially at the surface. Eventually there'll be a new equilibrium, but you can see the cartoon particles up here in this airspace are fewer than the cartoon particles in the airspace on the original beaker. Interesting. Here's another thought experiment, which you can do, but I've not actually honestly seen it done. You take some pure solvent and some solution. So maybe this is just water, maybe this is sugar water, and you put them in a sealed container and you let it come to an equilibrium. Well, this one evaporates and this one evaporates. The water evaporates from this and the water evaporates from this, but the water evaporates from this much more quickly. This is called a reduction in vapor pressure, so the water doesn't evaporate from this as quickly. And what ends up happening, legend has it, is that since the water evaporates from this beaker faster and fills the airspace of the jar, that pretty quickly this level increases and this level decreases. Maybe only because this isn't evaporating as quickly and more particles are in the airspace above it. And statistically speaking, they're more likely or probably going to recondense into this beaker. That's kind of pushing it if you ask me, but whatever. There's an equation that describes how the vapor pressure is reduced. So the pure solvent has some kind of vapor pressure. I think we mentioned it in a chapter on something last semester. What was it? Whatever. But anyways, there's a kind of a pressure measurable in, say, torr or atmospheres above a liquid that kind of pushes it up into the gas phase. For water, since it doesn't evaporate very quickly, this pressure of the pure solvent is small. But for something like an alcohol or an acetone, which are actually barely liquids at room temperature, they evaporate very easily, and this pressure will be greater. But as I dissolve some solute into the solvent, that decreases. So this pressure of the solution, the vapor pressure of the solution due to the solvent, is less than the vapor pressure of the pure solvent itself. And that reduction is simply the mole fraction of solvent multiplied times the original vapor pressure of the pure solvent. That makes no sense at all. Example. So water has a vapor pressure of 23.8 torr at this temperature. What temperature? They didn't say the temperature. It looks like room temperature. I think I know. Water has this vapor pressure, room temperature. But if I dissolve 99.5 grams of a simple sugar into 300 milliliters of water, how will that reduce that 23.8? Well, it won't be 23.8 anymore. It'll be less. But how do you figure that out? You simply compare the moles of sugar, change grams to moles, to the total number of moles. Here I'm changing milliliters of water into grams of water and grams of water into moles of water, and then I say this is the total number of moles of solvent and solute, and this is the moles of solvent. So the chi, the fancy capital X, the mole fraction of water, is the moles of water compared to the total number of moles, 0.983. So this reflects a reduction in a sense, the concentration of water. If you want to put it that way, it's not a molar concentration, but it is, let's say, less water or more sugar at the surface getting in the way of the water evaporating, so that vapor pressure comes down. Interesting. What's the total vapor pressure of a solution made by dissolving 25 grams of glucose in 215 grams of water at 50 degrees? We need to know what the vapor pressure of water is at 50 degrees. It's 92.5. So guess what? That's going to come down. But by how much will that come down? Well, you can see at one point I use this as a clicker, so if you feel like it, pause the video and try it yourself. And if you don't feel like it, here we go. How about this? So change grams to moles for the simple sugar, change grams to moles of the water, add them together, and say the mole fraction of water is the moles of water compared to the total number of moles. And again, it's close to 1. But so, unless your solution is very concentrated, which it could be, say concentrated acid or concentrated sugar water, this mole fraction of the solvent's usually pretty large, closer to 1, but not 1. If it was 1, then it would be 1 times 92.5, and we wouldn't have anything dissolved in the water anyway, so it would be just water and no solute. Interesting. Alright, whatever. Look at that. Think about it. Ask me a good question. What the... Sorry about that. There's another equation if you want to think about it this way as well. And it talks about how much that, to what degree that vapor pressure is reduced. So, in other words, the difference between this one and this one is described by the original vapor pressure of the solvent minus the vapor pressure of the solution, and that will give you the change. And that's also equal to the mole fraction of solute, which I don't usually say it this way, but you can say it this way. The mole fraction of solute, which is that other part of the mole fraction as a whole. So if my mole fraction of solvent was 0.9, the mole fraction of solute would be 0.1. 0.9 plus 0.1 is 1, and so the mole fractions have to add up to 1. Most students get a little bit confused by this equation, so I don't dwell on it too much. I like this one. That's a simple one. Oh geez, I hesitate to even show you this, but I will briefly. What if your solute also has a tendency to evaporate? So water and alcohol, or water and acetone, they both kind of evaporate, in which case the total vapor pressure would be equal to the vapor pressure of the solute plus the vapor pressure of the solvent, as described by these relationships. Solvent, 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 solute, solute, solute. This one plus this one equals the total pressure. And I think I'm going to skip over that pretty quickly, hinting to you that I don't usually see that much. Usually it's the solvent that's doing the dissolving, and the solute is not volatile. Volatile meaning it evaporates easily. So usually it's like sugar or salt in water, and that's getting in the way of the solvent evaporating, reducing its vapor pressure. So I'm going to kind of brush that one aside and say, look at it if you're super motivated. Otherwise, is this one? Oh, yuck. Ether and alcohol. So ether is a volatile, it evaporates easily. Liquid. Same for ethanol. So if you want another example of that, which I don't think we should worry about too much, but here's my ether and here's my ethanol, and the mole fraction of ether is 0.667, and the mole fraction of ethanol 0.333-ish. So it looks like 1/3 ethanol and 2/3 ether. So 2/3 times the total pressure, no, the original vapor pressure of ether, and 1/3 times the original vapor pressure of ethanol, and those are the partial pressures of the two. We could call this one solute and this one solvent, perhaps. Well, usually the solute's in smaller quantities, so let's call this one the solute, not the solvent, but it really doesn't matter. If they're both evaporating, they both contribute to the total pressure. One more consideration, which is interesting to think about. If I had a mixture of two things, column A and column B, so call them A and call them B, and I mix some A with some B, what happens to the partial pressure of each in the mixture? So if I had a mole fraction of, this is actually, I should have labeled this axis, this is the mole fraction of A. If I had only A, it would evaporate it to this extent. But if I had no A and only B, B would evaporate to this extent, as described by the vapor pressure of B. Interestingly, we draw a line connecting the two and say the total vapor pressure is the sum of this plus this, or this plus this equals this, or this plus this equals this, thinking vertically, or this plus this equals this, or this blue plus this red 0 equals this purple, and it connects up to give a straight line, vapor pressure of solution. But if those particles of solute and solvent actually interact more than you think they should, more than classically, more than usual, what's usual? We'd have to define that as well. But if they interact or are sticky upon and with each other, then they will actually pull on each other and kind of diminish the total vapor pressure or the partial pressures of each in the mixture. So the straight lines were what I just saw a second ago. But if those particles are interacting super duper much, a lot, and holding back, then there's not as much evaporation and the vapor pressures come down. Or conversely, if there is, by some description at least, a reduced interaction between the solvent and solute in some way, maybe we have to slow down and define that if we'd like, but if we have maybe a non-ideal solution where the particles are interacting not at all, or perhaps in a repulsive way in some sense, then there'll be more evaporation than I would predict, and this would deviate from Raoult's law. So this line is Raoult's law, and the law is sort of a descriptive approximation. It doesn't always match with what we see in the lab, but it is an approximation. So anyways, think about it, and I'll see you in class. Thanks for watching. Are you bored to tears yet?